Welcome to the video lecture series of Basic Electronics Engineering. Course code EC101, contact hour 3, credit 3. Myself, Dr. Shunipa Roy, Assistant Professor of Electronics and Communication Engineering Department, Guru Nanak Institute of Technology, Kolkata. Today we will learn Module 6, that is Cathode Ray Oscilloscope, CRO. This is Lecture 23. Let us first present the lesson plan. This is the lesson plan, operating principle of CRO with block diagram, measurement of voltage, frequency and phase. So let us start with the subject topic, that is cathode ray oscilloscope, CRO. A cathode ray oscilloscope is a multi-purpose display instrument used for the observation, measurement and the analysis of waveform by plotting amplitude along y-axis and time along x-axis. The measurement all are in time domain measurement. CRO is basically an XY plotter. On a single screen, it can display different signals applied to different channels. It can measure amplitude, frequencies, phase shift of various signals. Many physical quantities like temperature, pressure, strain can be converted into electrical signals by the use of transducers. As we know, the function of transducer is to convert mechanical energy into electrical energy, and that electrical energy can be measured or displayed on the CRO. Actually, a moving luminous spot over the screen displays are there in the CRO. CROs are used to study waveforms and other time varying phenomena from very low to high frequencies. The central unit of the CRO is the cathode ray tube, or we may call the heart of the CRO is CRT, that is cathode ray tube, and the remaining part of the CRO consists of the circuitry. Different types of circuitry is there, we will study later on, and that circuitry is required to operate the cathode ray tube. So moving to our next slide, this is the block diagram of a cathode ray oscilloscope, very nicely given. So this is left side is the input side and the right side is the output side. So what is there at the input side? Let us see. This is filament from which electrons are emitted. This is a heated cathode. After that, there are so many flow focusing electrodes or anodes, A1, A2. So this electron beam that is out from the cathode is actually distributed throughout this section. So first we need to focus that electron beam so that it can reach to the right hand portion, that is output section, easily without getting diffracted. So A1, A2 are the cylindrical focusing anode. This is made cylindrical to shape up the electron beam that is being emitted by the cathode. Next is different type of deflecting plates are there. One is vertical plate and second one is horizontal plate. So The interesting thing is that the vertical orientation, that doesn't always signify that this is vertical plates. Actually, this is called vertical plates, but the orientation is horizontal. This plate orientation is horizontal. And this plate, the second one, the orientation is vertical. But this is called horizontal plate. Why? Because the electron passing through these vertical and horizontal plates, see what is happening actually vertical plates. If we put a potential in this vertical plate, if we connect a potential difference in these vertical plates, what will happen? The electron beam passing through these vertical plates will experience a force towards up and down direction, and automatically it will move up or down. So the deflection will be vertical. But in this case, this X plate actually, when electron beam is passing through this X plate, what is happening? If we put or connect electric potential here, electron will experience a force while passing through these plates, and it will move left and right. So as a whole, the movement of the electrons are horizontal. So these plates are called horizontal. Isn't it interesting? Now, the electron passing through these vertical plates and horizontal plates reach out to the fluorescent screen. This screen is made fluorescent. An electron bombardment is there, and we see the final signal at the screen. Hope this is clear to all of you. We are moving to our next slide. So this is block diagram. Previous one also block diagram, but the main difference is that the circuit, all the circuit elements have been put here to make you understand how the CRO is working. So we can see, we know now this is electron gun, this is vertical plate, this is horizontal plate. Now what is happening? The electron passing through this vertical plate actually very weak signal. So we need to amplify this signal. So we have to add a vertical amplifier to this vertical plate. See what is happening? This is the input signal, and this is actually passed through the vertical amplifier, and then this amplified output actually has been connected to the vertical plates after passing through the delay line. We will study later why this delay line has been incorporated in the figure. Next thing is that after vertical amplification, the same signal is used to trigger circuit. Now the output of trigger circuit is nothing but the time-based generator. This is basically a sawtooth wave generator or RAM voltage generator. The output of time-based generator is connected to horizontal amplifier. So the signals are amplified again. This horizontal amplifier output is connected to horizontal plate. So this is the trigger circuit. This trigger circuit is it is used to trigger the time-based generator. If time-based generator is not triggered, then we will not get any horizontal deflection in the CRO. Now one more thing is that high supply voltage is applied to the body of this CRT. This is actually the cathode ray tube. So moving to our next slide, the CRO basically consists the following. That is CRT, cathode ray tube. That is actually a vacuum tube as previously used in electronic circuit. but presently we are using solid state devices. Cathode ray tube has been replaced by, or vacuum tube has been replaced by solid state devices. Next thing is vertical amplifier. This amplifier is needed to amplify the signal before putting it to the vertical plates. Next is delay line, because if you go to the previous slide, you will find that there is a delay line. Why this delay line is produced? See, after this vertical amplifier, if we put the signal directly to the vertical plates, what will happen? Electron will pass through these vertical plates, then again to these horizontal plates, and will reach to the fluorescent screen. It will be so fast. But the circuit here is trigger circuit and time-based generator. There is a delay. The signal that is passing through this section, there always be a propagation delay. So for proper synchronization of the signal in vertical plates and in the horizontal plates, a delay line has been incorporated in this circuit. So this is the function of delay line. Similarly, horizontal amplifier is nothing but the function same as vertical amplifier, to amplify the signal before putting it to the horizontal plates. Next is time-based generator. Time-based generator is actually sawtooth wave generator. Sawtooth wave generator is actually applied to the horizontal plates. Next is triggering circuit. After passing the signal, if we move to the previous slide, you will find that after passing the signal through vertical amplifier, time-based generator has to be triggered, because it has to know that now it is the time to activate myself. So this trigger circuit is used to trigger the time-based generator, and after that it is connected to the horizontal plate passing through the horizontal amplifier. So next is power supply. Power supply is the heart and soul of any circuit. It is needed to give the power to the circuit. So moving to the next slide, what is the function of power supply? It provides the voltage required by the cathode ray tube to generate and accelerate the electron beam. So cathode ray tube requires high voltage for pre-accelerating and accelerating anode. Low voltage required for heater, control grid, focusing anode, and other circuits of CRO. But high voltage is required for cathode ray tube. So vertical amplifier is the next section. The signal under the analysis is to be applied to vertical deflection plates through the vertical amplifier, so that it can be amplified properly and we can have the proper signal at the output. Next section is delay line. Let us elaborate what is delay line. Again, if both vertical and horizontal signal arrives at the same time to the corresponding deflection plates, then only we can get exact waveform. But the vertical signal arrives much early as compared to horizontal signal, as there are so many internal circuitry are involved. So to make it synchronized, the delay line has been incorporated after the vertical amplifier, so that it can give a time or a space to reach the signal to the horizontal deflection plates through the horizontal amplifier. The delay time is almost equal to 200 nanoseconds. So moving to our next slide, this is the trigger circuit. This is triggered by the portion of the vertical amplifier output. Actually, this circuit initiates the time-based generator, and it is the link between the vertical input and the horizontal time-based. Trigger circuit is used to synchronize horizontal deflection with vertical deflection. So moving to our next slide. The next is horizontal amplifier. So the sawtooth voltage produced by the time-based generator may not be of sufficient strength. So it should be amplified before putting to the horizontal plate. Hence, before giving it to the horizontal deflection plates, it is amplified using the horizontal amplifier. So moving to our next section. This is the cathode ray tube. So the electron gun or electron emitter, the deflecting system, and the fluorescent screen are the three major components of a general purpose cathode ray tube. A detailed diagram of the cathode ray oscilloscope is given in this figure. As already mentioned, this is the connecting pin, this is electron gun, this is vertical electrode for vertical deflection, this is horizontal electrode for horizontal deflection, this is the electron beam, this is the fluorescent screen. The fluorescent screen is made with the coating of phosphor, and this is the CRT, cathode ray tube. This is an ordinary vacuum tube. So moving to our next slide. In the electron gun of the CRT, electrons are emitted and converted into a sharp beam and focused upon the fluorescent screen. The electron beam consists of an indirectly heated cathode, a control grid, an accelerating electrode, and a focusing anode. The electrodes are connected to the base phase. The cathode emitting the electron is surrounded by a control grid with a fine hole at its center. The hole is very, very narrow. The accelerated electron beam passes through the fine hole. The negative voltage at the control grid controls the flow of electrons in the electron beam, and consequently the brightness on the spot on the CRO screen is controlled. Electrostatic deflection of an electron beam is used in a general purpose oscilloscope. So this is the mainly deflection system. The deflector system consists of a pair of horizontal and vertical deflection plates, as already shown in earlier slide. Now let us consider two parallel vertical deflecting plates P1 and P2. The beam is focused at point O on the screen in the absence of a deflecting plate voltage. If a positive voltage is applied to the plate P1 with respect to plate P2, the negatively charged electrons are attracted toward the positive plate P1, and these electrons will come to focus at point Y1 on the fluorescent screen. So this point must be noted that we have to apply a positive voltage at plate P1, otherwise electron will not move. This is the schematic of deflection system. The deflection is proportional to the deflecting voltage between the plates. This voltage is applied if the polarity of the deflecting voltage is reversed. The spot appears at point Y2. We are applying this side. P1 is connected to the positive terminal of the battery and P2 is connected to the negative terminal of the battery. In that case, we are getting, say, the deflection, electron beam deflection at point Y1. But if we reverse the direction, that means P2 is connected to positive terminal of the battery and P1 is connected to the negative terminal of the battery, in this electron deflection position will shift and we will be having a spot at Y1. So this is the basic function of the deflection system. Next is, the previous slide was for vertical deflection plate. This is elaborating the deflection through horizontal deflecting plates. Same thing is happening here. Here, two horizontal plates are there, H1 and H2. H2 is connected to the positive terminal of the battery and H1 is connected to the negative terminal of the battery. Electron beam are passing through this horizontal deflection plates. It is experiencing a force in horizontal direction and we will get a spot at point X1. When, say, no vertical deflection plates voltage is present. Now, if we reverse the polarity, this polarity, then we will get the deflection at point x1 rather than point x2. So moving to our next slide, this is the ultimate deflection showing, see, this is the input voltage applied to the vertical plate. This is a sine wave, and this is the input voltage applied to the horizontal plate. So vertical plates always connected to a sine wave, and horizontal plates are always connected to a sawtooth wave generator or ramp voltage generator. This ramp voltage is the key factor of any CRO. So what is happening? This figure shows as the wave applied to the vertical deflecting plate, sine wave actually applied to the vertical deflecting plate, and a repetitive ramp or sawtooth applied to horizontal deflecting plates, then electron beam will be deflected horizontally across the screen for horizontal plate, and also will deflected vertically across the screen for vertical deflection plates. Now what is happening? There are two forces are acting on electron, that is vertical deflection, horizontal deflection. So actually electron will experience a resultant force. For this resultant flow force, electron will move in this way, and it will be a replica of the voltage that has been applied to the vertical deflection plates. See, this is shown here, resultant display, and this is the screen, and x-axis is time, y-axis is voltage. Hope this is clear to everybody. Next slide is fluorescent screen. Actually, we should know what is the material we are using at the fluorescent screen. The material we are using, that is phosphor. Phosphor is used as screen material on the inner surface of a CRT. Phosphor absorbs the energy of the incident electrons. The spot of light is produced on the screen where the electron beam hits. The bombarding electrons striking the screen release secondary emission electron. And mind it, these electrons are collected or trapped by an aqueous solution of graphite called aqueduct. This is a coating, okay? Aqueduct is a coating which is connected to the second electrode. Collection of these secondary electrons is necessary to keep the screen in a state of electrical equilibrium. Otherwise, screen will get damaged. The type of phosphor used determines the color of the light spot. The brightest available phosphor isotope P31 produces yellow green light with relative luminance of 99.9%. There are different types of phosphor material used. So moving to our next slide, this is actually sawtooth voltage waveform and the time-based generator circuit output. So time-based generator is used to generate sawtooth voltage required to deflect the beam in horizontal section, not in vertical section, mind it. In sawtooth waveform, the deflecting voltage increases slowly and linearly with respect to time and reduces to zero quickly. That is, rise time is high and fall time is less. So we can see here that rise time is high. The time taken to reach the electron from this point to this point is quite larger than the time taken from this point to this point. That's why this is mentioned in the slide. So moving to our next slide. One more thing, mind it, why this is called sawtooth voltage waveform? Because it looks like a sawtooth, right? You have seen the sawtooth equipment, machinery equipment used to cut the wood or any type of solid material. It looks like a sawtooth. So moving to our next slide. type of cathode ray oscilloscope that has been used in the laboratory or in the industry. Analog CRO. In an analog CRO, the amplitude, phase and frequency are measured from the displayed waveform through direct manual reading. Generally, analog CRO are used in different laboratories in college, universities, where a very high-end measurement is not required. Digital CRO. Digital CRO offers digital readout of signal information, that is the time, voltage or frequency along with signal display. It consists of an electronic counter along with the main body of the CRO. And one more thing, digital CRO is costlier than analog CRO. Storage CRO. A storage CRO retains the display up to a substantial amount of time after the first trace has appeared on the screen. The storage CRO is also useful for the display of waveforms of low frequency signals. Now, dual beam CRO. In the dual beam CRO, two electron beams fall on a single CRT. The dual gun CRT generates two different beams. This is much more costlier. These two beams produces two spots of light on the CRT screen, which make the simultaneous observation of two different signal waveforms possible. The comparison of input and its corresponding output become possible by this dual beam CRO. Now, one more important formula, that is deflection sensitivity of a CRT. So, what is deflection sensitivity? That is the total current divided by the deflection voltage. The unit of deflection sensitivity is meter per volt. So, this is actually the length that has been covered on the screen by the deflection voltage. That's why the unit is meter per volt. And the deflection factor is nothing but the reverse of deflection sensitivity, that is volt per meter. So, moving to the next slide. So, what is the effectiveness of deflection sensitivity? The electrostatic deflection system uses a pair of deflection plates as shown in the figure as already mentioned in our previous slide. A hot cathode K emits electrons which are accelerated towards the anode by the potential VA. Those electrons which are not collected by the anode pass through the tiny anode hole and strike the end of the glass envelope. The glass envelope has been coated with a material that fluoresces when bombardment of electrons are there. Thus, the position of electrons we can see by our eyes. So, moving to our next slide. This is the electrostatic deflection system that has been mentioned in this figure. So, this is L by 2 and this is L by 2. This is phi, this angle is phi. This is anode N. And this is the L length that is mentioned in the deflection sensitivity portion. This small L and this capital L. And this is a deflection E. If we move to our next previous slide, we can see that this is the deflection E. On the basis of that, one can find deflection sensitivity. So, moving to the next slide, this is the formula. D equals to L into capital L into small l into Vd by 2 small d Va. Capital L is the length, this length. Small l is the this length. And D is the distance between the plates. Va is the anode voltage and Vd is the deflection voltage. So, this result shows that the deflection on the screen of cathode ray tube is directly proportional to the deflecting voltage VD applied between the plates. So deflection sensitivity of a cathode ray tube is defined as the deflection on the screen per volt of deflecting voltage. That's why the unit is meter per volt. Now one is magnetic type of deflection. Another point to be mentioned here. Here the magnetic field is perpendicular to direction of electron beam. The electron beam is deflected upwards. The electron moves in a straight line to point O from cathode with initial velocity 0. Now the force acts on the electron and the resultant direction is perpendicular to both B and B. Moving to our next slide, this is the magnetic deflection sensitivity, magnetostatic deflection of cathode. This is anode, this is cathode, voltage is applied and a magnetic field is applied between the vertical plates. So hope this is clear to everybody. So moving to our next slide, Lissajous method. This is very important phenomenon. The oscilloscope is a sensitive indicator for frequency and phase measurement. The Lissajous pattern results when sine wave are applied simultaneously to both pair of deflection plates. But the point is that one frequency is known and the another frequency is unknown. In that case, we use Lissajous method to find out the unknown frequency. So let us describe the things. This is the CRO. This is unknown frequency has been applied to vertical deflection plates and the known frequency that has been applied to horizontal deflection plates. The resulting pattern depends on the integral and phase relationship between two frequencies. So measurement procedure is that set up the oscilloscope and switch off the internal switch. Switch of sync control. Connect the signal source as shown in the previous slide. Set the horizontal and vertical gain control for desired width and height of the pattern. Keep frequency FV constant and vary frequency FH. Nothing that the pattern spins in alternate direction and changes shape. The pattern stands still whenever FV and FH are in an integral ratio. Say if the frequency of FH is 2 kHz, then the frequency of FV should be 4 kHz or 6 kHz. So this is the thing that pattern gets stand still when FV and FH are in the integral ratio. When FV equals to FH, when the two frequencies are seen, the pattern stands still and is a single circle or ellipse. When FV is greater than twice FH, a two-loop horizontal pattern is obtained. Here we can see different types of pattern. Here, this is the very important formula, that is FV by FH, that means vertical plate frequency by horizontal plate frequency equals to number of horizontal tangencies by number of vertical tangencies. So what is now vertical tangencies and what is horizontal tangencies? Say this is the pattern, this D pattern we are taking as for example, this is the pattern. So horizontal cutting point, there are 4 horizontal tangencies. If we draw a tangent line here, we will find that there are 4 horizontal tangencies. But the vertical tangencies, if we draw a vertical line here, vertical tangency here, we will see that there is only one point crossing the vertical tangency. So FP by FH equals to 4 by 1. So FP equals to 4 times of FH. Similarly, if we go to this section, say figure I, we can see that number of vertical tangents is 1, 2, 3, 4 and 5. 5. And number of horizontal tangents are 1. If we draw horizontal line and vertical line here. So FB by FH equals to number of horizontal tangents by number of vertical tangents. So number of horizontal tangents here 1, vertical tangents here 5. Now the formula is FB equals to 1/5 of FH. Now if FH is known, then we can easily find the value of FB. In this way, from Lissajous figure, we are getting the unknown frequency from a known frequency. All these are the examples of Lissajous figure. Scientist Lissajous has invented this. So as per the name of the scientist, this figure is called Lissajous figure or Lissajous pattern. So moving to the next slide, this is the application of CRO. Application of CRO is in radio network, in scientific and engineering application. There are so many applications associated with it, whether it is analog CRO, whether it is digital CRO. Digital storage oscilloscope is actually used in high-end laboratories, depending on the requirement and depending on the capacity, that is as the cost is varying. So CRO is used. Different types of CROs are used depending on the requirement and depending on the capacity. So if there is any question regarding CRO, you can ask me through mailing. Please mail me at shunipa.roy@gnit.ac.in. I will be happy to receive mail from you all. Thank you very much.